Hi, it's Paul Anderson, and in this video I'm going to talk about the synapse, which is a connection between adjacent neurons. That's a pretty strict definition. Remember, neurons can also be connected to effector cells in our body. But if we look at this neuron here and this neuron, the information has to get from this axon to this cell body or to this dendrite, and then the same thing down here. And we use synapses to do that. We're mostly going to be talking about chemical synapses in this video. In a chemical synapse, you have an action potential move down an axon. It triggers the release of neurotransmitters into this gap or this cleft right here. They're going to dock with chemically gated channels on the other side, and that can lead to an action potential on the other side. Some of the early work done with neurotransmitters was done by Otto Lowy. He had this dream of a wonderful experiment in the middle of the night dealing with the heart of a frog. He wrote it down, but when he woke up in the morning, he couldn't read his handwriting. Thankfully, he had that same dream again, and this is how the experiment that led to a Nobel Prize went. He had the heart of a frog that was beating, and then he would stimulate the vagus nerve on the surface of the heart, and what that does is slow the beating of the heart. So we're sending a message to the heart. He then took another heart from a different frog, but he removed the vagus nerve, so there's no neuron there. He got it beating, but he moved some of the liquid from the stimulated heart to the non-stimulated heart, and it slowed down as well. What did that mean? There was something in the liquid. He discovered these neurotransmitters, and he discovered a chemical synapse. In a chemical synapse, an action potential moves down a nerve, down a neuron. It triggers the release of neurotransmitters into the gap that are going to dock with receptors on the other side. Now, that's only one type of synapse. We also have electrical synapses. In an electrical synapse, an action potential is going to move down. And again, that's triggered by these voltage-gated channels. Once it gets to that synapse, it's going to open up more voltage-gated channels, and the message is going to go. An electrical synapse, if you have an action potential in the neuron before the synapse, you're going to have an action potential in the one after. What's great about electrical synapses is that they're very, very fast. What's bad about them is that there's no control. So let's talk about chemical synapses. To identify the different parts of it. So this would be where the information is coming in. So on this neuron, and this would be the cell body of the adjacent neuron. So we have a presynaptic side and a postsynaptic neuron. And then this little gap in the middle is going to be synaptic cleft. Now there are structures that hold this in place. It's not just floating there. On the inside of that terminal bud, we have synaptic vesicles, and those are filled with neurotransmitters. Those are different chemicals, chemical messages that can be sent across that synaptic cleft. There's some other anatomy that we should cover. There are going to be voltage-gated channels on the terminal bud. Those are going to be calcium ion channels. We also have docking proteins for vesicles on the presynaptic side, and then we're going to have receptors on the postsynaptic side. And so if we remove all of those terms, let's see what happens. So first thing that happens is we have an action potential that's moving down this neuron here. If you don't understand what an action potential is, I'll put a link to a video that I made on those. So the action potential comes down, and what that's going to do is the depolarization of that neuron is going to open up these calcium voltage-gated channels. Now the electrochemical gradient for those calcium ions is into the neuron itself, and so they're going to move in, and they'll dock with chemicals on the surface of those vesicles. They're going to activate proteins on those surfaces, and what allows those to do is to connect with other docking proteins on the surface of the presynaptic side, and allows those vesicle membranes to merge. They then dump their neurotransmitters out into the gap where they can dock with these chemically gated channels on the other side. So they're sending a message through those neurotransmitters. Now the neurotransmitters will quickly then break apart. Some are broken down, some are recycled back into those synaptic vesicles. But let's see what's going on. So there are a number of different channels in every neuron. There are going to be leak channels for sodium and potassium. What those do is establish this resting potential. We also have voltage-gated channels. Those are important in the transmission of that action potential. But here we're talking about receptors. These are chemically gated channels. So when the neurotransmitters gap with it, they can open it up. What does that do? Well, it can move us towards or away from an action potential. So an action potential is when we hit this threshold of negative 55 millivolts. That's determined by these voltage-gated channels. But what can happen in an excitatory neurotransmitter, and a neurotransmitter that's pushing us towards the threshold, is that it is increasing the voltage. It's moving it closer to that threshold. What's a quick way to do that? If we have a receptor on the postsynaptic side that allows the flow of sodium into the neuron. That sodium is quickly going to depolarize the neuron and move us closer to the action potential. Now, some of those neurotransmitters may be inhibitory. What they're doing is they're allowing the flow of ions, but these are ions that are moving us away from that action potential. What's a quick way to do that? We could release a bunch of potassium or allow chloride to come into the cell itself. But if you think about it, a neuron is then receiving information from all the neurons that are connected to it that are telling it to either fire an action potential or not. What are they really doing? They're sending either excitatory, those are depolarizing messages, the influx of sodium that is starting to trigger an action potential, or inhibitory. Those are ones that are allowing potassium out or chloride in, and they're stopping that message from being sent. And so we really have an analog side to a neuron and a digital side. The summation of all of those signals, all those neurotransmitters, either tell that action potential to fire or not, and it's going to move down that axon. Now remember, when we get to the end, there are going to be terminal buds here. Again, calcium gates are going to open up, and we're going to have those new neurotransmitters that are sent across. Now, when you remember things, so if you can remember things early from this video, a lot of that has to do with connections in neural pathways in your brain. And what we're starting to find is that when you really remember something, that as we fire action potentials, as we have more of these synapses being activated, what we have is long-term potentiation. And so if we look at what's going on here, if we keep firing this neuron, we've done this in the lab, we keep firing and releasing neurotransmitters. On the postsynaptic side, the cell will actually develop and build more of these receptors, so it's more susceptible to that. And so we're building pathways of memory over time, and that's really what memory is. It's a set of neural pathways that are firing inside your brain. So that's the chemical synapse, and if you can remember a lot of the parts on this pre- and postsynaptic side, you're well on your way to improving your memory, and I hope that was helpful.